So if you stop and think about the cameras and sensors we rely on today, the array in your phone, maybe a massive medical scanner, even the optics that make your VR headset feel so heavy, they all rely on some variation of, well, bulky, curved glass or maybe expensive, specialized crystals. Imaging today is incredibly powerful, don't get me wrong, but fundamentally, it's often slow and physically cumbersome.
Exactly. And our sources today describe a world that's really on the verge of shedding that bulk entirely. They paint this picture of a radical, sort of three-pronged revolution in how we capture light and radiation. And this transformation is being driven by, well, high-speed transformative AI, new crystal technologies like Perovskites, and these exotic ultra-flat nanophotonics.
That's what we are here to unpack today. We're doing a deep dive into the latest medical imaging trend reports, some breakthrough studies on next-gen detector materials, and the really ambitious roadmap for flat nanostructured optics. Our mission is pretty clear. We want to give you the shortcut to understanding how the world is about to see differently. I mean, from atomic scale metrology, we're talking femtometer resolution, all the way up to revolutionary cancer scans.
Yeah, we're pulling the critical nuggets of insight directly from the research, showing you not just the facts, but importantly, the implications and the place where the impact is going to be felt first, and you could argue greatest, is in healthcare. So let's maybe start there with the 2025 medical imaging revolution.
Okay. And the most immediate shift isn't just about faster machines, interestingly. It seems to be a philosophical shift toward health equity and access. We're seeing this monumental push to address healthcare disparities, mostly by making sophisticated imaging available far outside the walls of, say, major city hospitals.
And what's fascinating here is how technology is really the primary driver of that expansion. Think about mobile imaging solutions, teleradiology, cloud-based platforms. These aren't just minor tweaks, right? They fundamentally allow analysis to happen instantly and remotely. That ensures timely diagnoses for patients maybe in rural or underserved areas.
And crucially, these cloud platforms, they don't just facilitate remote viewing. They are the delivery mechanism for the most sophisticated AI, aren't they?
Absolutely. The ability to deploy complex generative AI models instantly, regardless of the physical location of the scanner, that's critical. And this AI is moving far beyond simple computer-aided detection. We're talking about models that can perform automated reporting, detect really subtle anomalies a human might miss in a high-volume setting, summarize vast patient histories in seconds, and even predict how a specific disease might progress under different treatment protocols.
Wow. So generative AI isn't just helping the radiologist spot a tumor, it's actually helping them write the report and plot the future of the patient's care path. Is that right?
Precisely. It's augmentation, not just assistance. And the good news here is that faster regulatory approvals seem to be accelerating the clinical adoption of these AI tools. This means radiologists can offload some of that routine, repetitive work, allowing them to focus their, highly specialized skills and deep experience on the most complex, ambiguous cases, the ones that really require human interpretation and empathy.
Okay, that makes sense. And this shift toward precision, it feeds directly into the drive for highly personalized medicine, doesn't it? Imaging is finally maybe moving away from the one-size-fits-all model that sort of defined diagnostics for decades.
That's right. The push is definitely toward tailored diagnostics, especially in complex areas like oncology, cardiology, and neurology. AI is now sophisticated enough to adapt to the actual scan protocols, like the way the machine operates, based on individual patient factors. That includes known risk factors, even genetic data.
How does that look practically, though? Is it just making the image better, or is it like integrating different types of patient information?
Oh, it's the integration that's the real game changer here. We're seeing the rise of these multimodal AI platforms. So these aren't just looking at the MRI scan, right? They're integrating diverse data streams, things like clinical notes, lab results, genetic sequencing data, with the imaging data. And that creates a truly comprehensive kind of 360-degree view of patient health. That holistic approach makes the diagnosis much more robust.
And underpinning all of this software innovation are actual hardware breakthroughs, making the scans themselves faster, safer, higher quality. We're seeing major moves in, I think, 3 key areas you mentioned: photon counting CT, digital SPECT, and whole body MRI.
Yeah, the one I think is potentially most transformative is photon counting CT, or PCCT. See, traditional CT scanners measure the bulk energy deposited by X-rays. PCCT, like the name suggests, counts every single photon that hits the detector, and it measures the energy level of each one individually. That's a massive improvement.
So we're going from almost an analog estimation to digital precision. What's the ultimate payoff for the patient then?
Well, it's twofold, really. First, You get significantly higher resolution, which means spotting smaller, earlier indicators of disease, much earlier. And critically, you can achieve that high resolution with a much lower radiation dose.
Hmm.
That makes the procedure safer, especially for routine screenings. And similarly, we are seeing digital upgrades to single-photon emission computed tomography or digital SPECT, which improves nuclear medicine quality quite a bit, and also more efficient, more affordable, whole-body MRI units for early detection, which were previously pretty cost-prohibitive for widespread use.
That discussion about improving detector materials and getting higher quality scans leads us perfectly to the next breakthrough. This one's fundamentally changing how we capture radiation. We need to talk about the crystal that famously transformed solar energy and is now ready to shake up nuclear medicine, perovskites.
Indeed. We've all seen the success story of perovskites in driving down the cost and boosting the efficiency of solar panels. Now, the source material we looked at details the first successful perovskite-based gamma-ray detector that seems ready for clinical use. This is pretty monumental for SPECT imaging, which relies on detecting gamma rays.
Okay, for our listener, maybe remind us why the detector material is such a critical bottleneck in SPECT imaging right now. What's the issue?
Well, because today you face this really painful trade-off. Your option for high precision is cadmium zinc telluride, or CZT. It's incredibly accurate, yes, but it is notoriously fragile and staggeringly costly. We're talking camera systems running into the millions of dollars sometimes. Your cheaper alternative is sodium iodide, or NaI, but that produces blurred, kind of foggy images that require a lot more signal processing afterwards.
Right, and the perovskite camera, as they call it, it sort of bypasses that trade-off entirely, offering a high-precision, low-cost solution.
That's the promise, exactly. It allows for SPECT scans that are sharper, faster, cheaper, and safer. Faster scans mean shorter, more comfortable times in the machine for the patient, which is great. And safer means lower radiation exposure simply because the detector is more efficient at capturing the signal in the first place.
Okay, wait a second, though. If perovskites were primarily known for solar, and those materials often suffer from stability issues, right?
Yeah.
Especially with moisture or heat, which is definitely not what you want in a demanding medical environment. How did the researchers stabilize this for clinical use? Is that like a solved problem now, or is it still a constraint?
That's a crucial question, and the sources address it directly. The stability challenge, it seems, was tackled head-on in the engineering phase. The researchers achieved the necessary uniformity and stability in the specific crystals they used, these CSPB-Ar3 crystals, through very careful chemical-mechanical surface processing. This technique was absolutely essential for eliminating surface defects, which are the main culprits for instability in these materials. By perfecting the surface, they achieved near-unity charge collection efficiency. So it proves that the preparation science, the manufacturing, is just as vital as the material chemistry itself.
Okay, that's a key piece of information then. It's not just the crystal, it's the process that makes it viable. Let's talk precision. The detector achieved a record energy resolution of 2.5% at 141 keV. What does that number actually signify?
Well, in nuclear medicine, 141 kiloelectron volts, or keV, that's the specific emission energy of technetium-99 meter. That isotope is the most widely used radioactive tracer worldwide, used in millions of scans. So the fact that the perovskite detector achieved 2.5% resolution at that precise energy means it can very accurately distinguish between different gamma-ray emissions. It gives you a much cleaner, much more informative signal compared to the existing alternatives.
And the practical result of that?
In phantom imaging tests, so not yet in humans, but in test objects, the spatial resolution was excellent, about 3.2 to 3.8 millimeters. It could distinguish sources that were spaced just 7 millimeters apart. So this level of detail, delivered by what promises to be a cheaper, more robust material platform, that's what could truly democratize high-quality nuclear medicine.
That's a fantastic transition point, actually, because now we're zooming out from these specific medical crystals to the flat optics that might define everything from, say, your phone camera to your VR goggles in the future. We're moving into the realm of nanophotonics and metasurfaces.
Right, metasurfaces. You can think of them as the next generation of lenses. Instead of relying on bulk curvature like traditional glass lenses, they are ultra-thin, engineered, planar arrays, like flat sheets. And they're covered in these microscopic nanostructures. Each tiny structure, often smaller than the wavelength of light itself, acts like a tiny antenna, basically manipulating the light that passes through it in very precise ways.
So essentially, we replace a heavy, curved stack of glass with a thin film. What's the primary optical problem they solve? The one that required all those curved layers in the first place?
It's the age-old problem of chromatic aberration. If you shine white light through a simple curved lens, different colors, red, green, blue focus at slightly different points, this mirrors the image, right? It requires complex stacked compound lenses, those heavy curved elements, just to ensure that every color focuses perfectly on the exact same spot.
Which is precisely why the camera bump on your phone is still there and why high-end VRR headsets can feel like, well, wearing bricks on your face.
Exactly. So the breakthrough of the sources describe is a single flat metal lens that can focus the entire visible spectrum, all the colors, onto one precise point. This is huge. It offers a simple, flat, wafer-thin replacement for those bulky lens stacks that could dramatically reduce the size and weight of devices like, well, advanced AR goggles, cameras, you name it.
And these flat optics are also enabling the next leap in display technology, holographic projection. The sources describe integrating these metasurfaces directly with OLED screens. That sounds interesting.
Yeah, this is a fundamental reversal, almost, of traditional holographic technology. Historically, creating detailed holograms relied on expensive lasers. You needed coherent light. But that inevitably introduces speckle noise, that grainy, shimmering look that really reduces the realism of the hologram.
Okay, so what's the advantage then of using OLEDs with metasurfaces instead?
Well, OLEDs produce incoherent broadband light. It's much easier to manage, much cheaper to fabricate the source. By integrating the metasurface, you can use the cheap, reliable, and importantly, speckle-free light from a standard display technology to create these vivid, high-fidelity holographic projections.
That seems like the ideal path for consumer adoption, right? Leveraging existing, mature manufacturing.
Exactly. This platform has a flexible form factor, potentially low power consumption. And because OLED fabrication is so well established, it feels like it's fast-tracked for mass-market consumer electronics, maybe augmented reality devices, even wearable holograms down the line. It solves a crucial manufacturing and user experience problem simultaneously.
Okay, so we've covered the future of health diagnostics, the future of consumer displays. Now let's head to the extreme edge. Computational imaging and picophotonics. This is where optics meet software, and the precision starts measuring things smaller than atoms.
Right? Computational imaging, or CI. This is the deep marriage of meta-optics and smart software. The core idea is actually radical simplicity. Use a dramatically simplified optical front end, maybe just a single, inexpensive flat metal lens. And then let a powerful computational backend, the software, sort out all the image processing complexity.
Huh. It sounds almost like a way to cheat physics, like making a less than perfect lens work better than a perfect traditional lens through software.
That's effectively what it is, yeah. And the payoff is dramatic reductions in size, weight, and power consumption across all sorts of imaging platforms. Where is that finding real-world impact right now? Well, look at the most demanding environment, autonomous vehicles and robotics. Specifically, the need for high dynamic range, or HDR, cameras.
Why are autonomous vehicles the ultimate test for dynamic range? What's the challenge there?
Because their sensors have to handle these huge real-time variations in light levels. The sources mention up to 180 decibels. To put 180 dB in perspective, you're asking the sensor to transition instantly from near total darkness, like driving out of a tunnel, to being absolutely dazzled by the brightest sunlight reflecting off snow or maybe wet pavement. That's like a billion-fold difference in brightness. Traditional systems really struggle with this, but CI systems, co-optimized with software, are vital for processing those extreme luminance ranges robustly, in real time, to prevent safety-critical mistakes.
That's a very practical, potentially life-or-death application of computational optics. But let's talk about that almost unbelievable atomic scale resolution you mentioned earlier. First, there's a revival of an older concept.
Yes, the lens-free mid-infrared pinhole camera. Researchers are reviving it, but applying it specifically to the mid-infrared spectrum. This allows them to identify heat signatures and molecular fingerprints without needing complex, heavy, and often fragile IR lenses. It offers a much larger depth of field, too, so it simplifies identifying materials based on their specific heat signatures or spectral properties.
Okay, and finally, the smallest ruler we've ever seen, picophotonics. We're dealing with metasurfaces enabling metrology at an almost, well, unbelievable scale here.
This is really where nanophotonics pushes well past traditional engineering limits. By using topologically structured light, specially patterned light interacting with metasurfaces, researchers have created what they call an optical ruler. It's capable of detecting the displacement of nanoscale objects with ultra-high accuracy. The resolution reported is better than 5,000, lambda over 5,000.
And what does that mean practically? How do we even visualize that scale, lambda over 5,000?
Well, when we say 5,000, we mean we are measuring features or movement that are 5,000 times smaller than the wavelength of the light we're using to measure it. To put that in perspective, the measured absolute error in these experiments reached down to just a few tens of femtometers.
Femtometers. Okay, that sounds impossibly small.
It really is. A single silicon atom, right, a common building block of technology, is about 220 picometers in diameter. A femtometer is 1,000 times smaller than a picometer. So we are not just detecting the presence of an atom, we are accurately detecting the movement of objects at a tiny, tiny fraction of the size of that atom. This really moves us out of typical engineering and more into quantum-level precision for fields like material science and micromanufacturing.
Wow. That really brings us full circle and illustrates the sheer breadth of the change we've covered today. I mean, we started with AI redefining hospital workflows and new perovskite crystals, making things like specky scans safer and cheaper. Then we moved to nanostructured flat lenses, potentially transforming displays into immersive, speckle-free holograms. And we finished with nanostructures providing atomic-scale metrology that can measure movement below the size of a single atom. It's incredible.
The sheer breadth is the takeaway, I think. The core thread connecting every source we looked at is this ability to engineer materials and control light and radiation at the nanoscale with just unprecedented precision. The future of imaging isn't really about better curved glass anymore. It's about structured matter and computational intelligence working together.
So the final question then is, what happens when these incredibly powerful fields fully converge?
Yeah, that's the most provocative question, isn't it? We have AI that's accelerating the inverse design of these complex metasurfaces, designing the structures faster than any human possibly could. At the same time, materials like perovskites and advanced manufacturing techniques are driving down the cost of high-resolution detectors. This combination strongly suggests that the next generation of high-end diagnostics won't just stay confined to the hospital wing for long.
Meaning the technology moves out into the hands of the consumer.
Exactly. You have to ask, will cheap, compact, multifunctional imaging sensors capable of chemical identification, high-resolution diagnosis, depth mapping, all sorts of things, will they be integrated directly into consumer devices or maybe wearables within the next decade? The technology seems to be moving rapidly toward making the world effectively transparent to us. We're about to see things in a whole new way.